For 4,500 years, the Great Pyramid of Giza has stood as one of the greatest engineering feats in human history. It contains 2.3 million stone blocks, each weighing several tons. The fundamental question isn't who built it, but how, with primitive tools, a tight timeline, and zero margin for error. We've been taught the ramps, but that's only part of the story. Today, the Analytical is going to perform a deep dive on the logistics, the science, and the cold hard math to uncover the real, most plausible construction method. The time challenge, a problem of logistics. First, let's consider the problem of time. Pharaoh Khufu reigned for approximately 20 years. To complete the Great Pyramid within that tight 20-year span, the sheer pace required of the workers is astonishing. Based on estimates, they would have had to place a massive stone block every 2 to 3 minutes. That's an average of 12 blocks per hour, operating for 10 hours a day, 365 days a year. Clearly, completing the pyramid wasn't merely an engineering feat. At this speed, it was primarily an extraordinary logistical challenge. The labor challenge, a shift in understanding. Next, we address the question of labor. Archaeological analysis has allowed us to move past the old myth of slaves. Discoveries, such as the tombs of the workers themselves, point instead to the use of highly skilled labor. This analytical shift prompts the question: how many people were truly needed to sustain such a massive undertaking? The current archaeological estimate puts the necessary workforce at between 20,000 and 30,000 people. The first part of the problem is the sheer scale. The Great Pyramid contains roughly 2.3 million individual stone blocks. Now, these aren't small garden rocks. The average block weighs about 2.5 metric tons, and the large granite blocks used in the king's chamber weigh up to 80 tons. Think about that, 80 tons. That's heavier than a modern Boeing 737 aircraft. The Egyptians had to quarry these massive stones, move them hundreds of miles from the Tura quarries, and then lift them hundreds of feet into the air. The time constraint. This is where the cold, hard math of the Analytical kicks in. Pharaoh Khufu's reign lasted approximately 20 years. If we assume they worked 10 hours a day, 365 days a year, for 20 years, they had exactly 7.3 million man-hours to work with. To finish the pyramid on time, the entire workforce had to quarried, shaped, transported, and placed one block every 2 to 3 minutes. This isn't a problem of sheer strength, it's a monumental logistics and management challenge. How do you move millions of people and millions of tons of stone with such relentless precision and speed, without modern machinery? The precision paradox. And here is the paradox. They had to maintain that speed while achieving near-perfect precision. The pyramid's 4 sides are almost perfectly aligned to the cardinal points of the compass, north, south, east, west, with an error margin of less than 1/15 of a degree. Furthermore, the base corners are almost perfectly level. How did a civilization without modern surveying equipment, lasers, or even the wheel, for heavy loads, achieve this level of astronomical and geometrical accuracy under such extreme logistical pressure? This is the core problem we must solve analytically. Hypothesis 1, the straight ramp. Let's begin with the most straightforward, intuitive solution, the straight ramp. This hypothesis suggests that a massive, linear ramp was built extending straight out from one side of the pyramid, gradually ascending as the structure grew taller. From an analytical perspective, this sounds simple, but it quickly runs into a significant mathematical problem. To reach the Great Pyramid's original height of 146 meters, 480 feet, while maintaining a manageable incline for dragging heavy stones, let's say a 9-degree slope, which is already steep, this ramp would have needed to be over 900 meters, almost 3,000 feet, long. Now, here's the kicker: the sheer volume of material required for such a ramp would have been greater than the volume of the pyramid itself. Imagine building a mountain of sand and rubble just to build another mountain of stone. This is not only incredibly inefficient but also leaves virtually no archaeological evidence of such a colossal structure. The logistics of building, maintaining, and then dismantling this monster ramp would have been a project on its own. Hypothesis 2, the external spiral ramp. Recognizing the impracticality of the straight ramp, engineers proposed the external spiral ramp. This theory suggests that a ramp spiraled up the outside of the pyramid, wrapping around all four faces like a coiled snake. Again, from a logistical standpoint, this seems more plausible as it requires less overall material than a straight ramp. However, when we apply analytical scrutiny to the construction process itself, major flaws emerge. The Great Pyramid is renowned for its near-perfect geometrical precision. Its four faces are incredibly flat, and its corners are remarkably straight and true, meeting at a single, incredibly precise apex. If a ramp were constantly hugging these corners, wrapping around the entire structure, how could the builders possibly maintain this flawless geometry? The ramp would obscure their line of sight, making it almost impossible to continuously verify the angle, flatness, and alignment of the pyramid's faces. It's a fundamental visual obstruction problem for precision architecture. Hypothesis 3, the internal ramp. This brings us to a more intriguing and scientifically supported hypothesis, the internal ramp. This theory, championed by the French architect Jean-Pierre Houdin, proposes that the bulk of the blocks were hauled up a ramp built inside the pyramid's body as construction progressed. From an analytical perspective, this solution immediately addresses many previous issues. Firstly, it uses far less material for the ramp itself, as the pyramid structure is the ramp structure. Secondly, it keeps the outer faces clear, allowing builders to maintain their line of sight and ensure the extraordinary precision we see today. The blocks could be turned at the corners, using small, flat landing areas. Crucially, this isn't just theory. Scientific evidence backs this up. In 1986, a French team used microgravity analysis to detect anomalies in density within the pyramid. Specifically, they found a less dense, almost hollow path spiraling upwards just beneath the surface in the corners of the pyramid. This exactly matches the predicted path of an internal ramp. It's an archaeological detection of an internal structure consistent with the hypothesis. While the internal ramp offers compelling evidence, it's unlikely to be the sole method. The construction of the Great Pyramid was a monumental task requiring an integrated system of solutions. Next, the Analytical will piece together the most plausible, multifaceted answer to how this ancient wonder was truly built. The Analytical conclusion is this: the Great Pyramid was not built using a single, monolithic ramp. Its construction was a masterpiece of integrated engineering, a complex, adaptive system designed to maximize efficiency under a brutal time constraint. The genius of the ancient Egyptians lay not just in architecture, but in project management and logistics. Phase 1. The foundation and the base. For the first third of the pyramid's height, the immense base, the straight, short external ramp was almost certainly used. This phase involved the largest volume of stone but the least amount of vertical lift. The external ramp allowed for wide, stable access, accommodating the massive workforce required for the base layers. However, as the pyramid rose past 50 meters, the straight ramp became logistically impossible, demanding a shift to a new method. Phase 2. The core structure. This is where the internal ramp hypothesis takes over. Our analysis of the density anomalies strongly suggests that the middle two-thirds of the pyramid were constructed using a spiral ramp built into the core. This allowed the continuous hauling of stone blocks upwards, without obstructing the outer faces. This method solved the precision paradox we discussed earlier. Builders on the exterior, working on the finished casing stones, could continuously monitor the geometry and levelness of the faces, ensuring that near-perfect alignment that still amazes us today. Phase 3, the peak and the capstone, simple mechanics. For the final phase, the last few meters, and crucially, the placement of the legendary capstone, the internal ramp may have become too narrow or steep. For this final, critical lift, simple, well-documented mechanical devices were likely employed, pulleys and levers, or a system of chauffeurs, counterbalanced lifting devices, working in sequence. This final stage required fewer blocks but the highest level of precision and risk. When we look at the monumental achievements of the ancient world, like the Great Pyramid of Giza, we often marvel at the scale and the engineering. We search for esoteric knowledge or alien intervention to explain the inexplicable. However, the most profound secret is often the simplest and the most human. The real genius, management. Ultimately, the answer isn't a single tool or a secret technology. It is the mastery of logistics, resource allocation, and quality control. The Egyptians had to manage 30,000 highly specialized workers, coordinate hundreds of quarrying teams, and ensure an uninterrupted supply chain of stone, all timed perfectly to place a block every 2.5 minutes. The Great Pyramid is a testament to the power of human organization and analytical planning. It is perhaps the first and greatest example of large-scale integrated project management in history. So, the mystery of the pyramids isn't about aliens or magic, it's about incredible human ingenuity, applied logic, and massive scale management. Which historical marvel should we analyze next? The Antikythera mechanism? The Roman roads? The collapse of the Maya civilization? Let us know in the comments below. If you want more deep dive analysis and critical thinking to see the world differently, hit the subscribe button for the Analytical.